Hi, I'm just going to quickly go over the solve function. So right here we set up our linear system of equation ax equals b, where x is the g values and exposure intensity values, log of them. We iterate through the number of pixels and across the different exposures, number of images. We then get the g of z value, put that into our system of equation. We get our ln e of I value, put that into our system of equations, and we also get the b value, which is then multiplied together and put them into our system of equations. We don't want to increment the row counter, so it just keeps track of the current row and equation. This is just the smoothing constraint, which penalizes large second derivatives. And then finally, we want to solve ax equals b, the least squares problem, or the least squares solution to the linear system that we have, and then extract the different values from our solution to return g and le. Moving on to HDR, we want to choose the middle exposure because it's the least likely to be over or underexposed, and we choose that for the alignment. And then this is just setting up, reading in the images, setting up HDR, setting up the weight sum so that we can normalize later. We want to iterate through the different exposures. We want to align. This is the same alignment algorithm I used in project 1. We then want to calculate the pixel weights for each channel. This is using the weight mapping. Then we want to, this basically just rearranges this equation into this equation, just some algebra, and just, finds the red log gradients, green log gradients, blue log gradients. Then we want to multiply things we calculated together to get the weighted log gradients, accumulate the weighted log gradients across the different exposures, and then also accumulate the different total weights, so that finally, after all that, we can normalize by the total weights, and then go from, we're currently in like log land, so we want to go to linear by exponentiating everything. Moving on, these are the tone mapping functions, which help, convert everything into things that can be displayed on our screen from 0 to 255 intensity values. So here is very simple. It just scales everything. So the smallest pixel value will be 0, and then the range is now max minus min, and then you divide by that to make the range. It forces the range to be from 0 to 1. This is a simple tone mapping function from Reinhardt et al. Just literally the equation right here. And then for the Durand function, this basically preserves like the local contrast, but it kind of compresses everything else. So we have it gives in our HDR radiance map, calculates the average intensity, calculates the chrominance levels by dividing everything by I, finds the log intensity, then it computes a base layer with a bilateral filter, basically preserving all the edges and local contrast, and kind of like blurring everything, all the uniform parts of the image out. So that would be our base layer. We want to normalize it, and then we have a detail layer, which has all the local contrast things that we're interested in. Then we want to apply an offset right here and scale to the base layer. We reconstruct the log intensity so that we can add the colors back. And then finally we stack the different colors or the different channels together to get our final tone map image, and apply gamma compression. And then something that came up was I found that if you're scaling by the brightest pixel, sometimes the image would turn out too dim, so I just scaled by the like second or 98th percentile brightest pixel. So it helped with the quality of the image. Okay, so I'm just gonna run it, show that it works. Yeah, so this is for the garden. We can do for chapel. And this is the image alignment algorithm that you can see here.